A little bit about swarm robots. We're interested in swarms because they offer robustness. If you have many robots working together, one robot failing may not be the end of the task. The other robots may be able to take over. Conversely, if you have a single robot, that robot failing is a big deal. Also, swarms may offer scalability. If you have many robots cooperating to accomplish a task, you may be able to do more by simply adding robots. However, this comes at the cost of communication. You can see on your screen that all 5 of these drones are communicating. There's lots of data flowing in and out, and the networking can be a challenge. Also, more robots means more opportunity for collisions. Now, what I'd like to show you is an example of another environment. This is now a constrained environment. We're looking at an example where there's 3 drones flying, and they actually have to fly through a narrow constrained opening. Now, this opening is represented by these orange boxes. So when I tell the robots to fly, they'll execute one of our approaches. Namely, they'll exercise the model predictive control method that we've implemented. This is an optimization-based method, and you can see that the drones sped through while maintaining their formation before landing. This is a centralized method because all of these drones' actions are planned at the same time by the optimization. From here, I'm going to introduce my colleague Ethan, who's going to show you one of our decentralized methods.
Thank you, Michael. I'll now show a demo of our approach on stage 3. This stage is meant to mimic forest traversal, which can be extremely useful in search and rescue applications. Environments such as this are difficult to traverse because obstacles are spaced irregularly, making it hard to maintain a rigid formation. Also in the forest, the drones need to respond quickly and independently to nearby obstacles to avoid crashes. The drones utilize the scaling ability of our Laplacian approach to avoid cylinders and then regroup at the end. This approach is decentralized because the follower drones have limited communication and only react in accordance with their leaders. This approach builds 2 graphs which encode information about the drone's positions and velocities and forms an ordinary differential equation to enforce a certain formation shape. Centralized approaches, like MPC, rely on a central controller with knowledge of the environment and drones, while decentralized methods operate locally with limited communication or global awareness. We've now looked at 3 different stages with static obstacles, and these stages, both centralized and dynamic approaches, perform well. Centralized approaches may have the edge though. However, environments with dynamic moving obstacles may be more difficult for centralized approaches. My colleague Maria will now show you a decentralized approach in a dynamic environment.
Thank you, Ethan. So here we can see the decentralized potential field approach executing stage 4, where we have dynamic obstacles moving around. The stage can resemble a scenario of drones surveilling environments like warehouses, streets, or other places with moving objects. In potential field approach, every drone is treated as a point under the influence of a potential field. Each drone is pulled by the attractive forces towards the end goal or to other drones if being far away, and is pushed away by the repulsive forces from the nearby obstacles and other drones if being too close. Now let's dive a little bit into the performance analysis of each stage. For our analysis, the success rate for each stage for each method was measured over 5 consecutive runs. For stages 1, 2, and 3, with static environments, all methods performed decently well, with MPC outperforming in time and formation accuracy. Potential fields struggling more with 5 drones due to accidental collisions. The major reason being the complexity of tuning the scaling coefficients for attractive and repulsive fields so that they can adapt and perform safely in different environments. For stage 4, MPC started to deteriorate and, though still maintaining high speed, sufficiently decreased in accuracy. This is because the environment is not fixed anymore, trajectory recomputation becomes expensive and leads to control lagging and eventual collisions. Potential fields performed consistently well, however still maintaining lower speed. In conclusion, we can say that the choice of the most suitable control method for swarm highly depends on the anticipated environment. For missions in static environments, MPC appears to be the most effective approach. On the contrary, in missions with dynamic environments and moving obstacles, the centralized methods may outperform. In future work, hybrid approaches could be explored that combine predictive capabilities of centralized methods with the reactive obstacle avoidance of decentralized methods to create a more resilient control system. That's it. Thank you for your time.